Welcome back to Chem 400. Announcements on Wednesday. You'll have exam 1. It'll start at 12:30. It will end at 2 p.m. That's 90 minutes. Those of you who are in study groups, I need you to turn in a photocopy of your study group logs. All that needs to be is date, times, who came, and topics for all of your study sessions so far. And if you remember from the syllabus, if you meet once a week for 2 hours or more, at least in a group of 2 or more, then you are eligible for a larger amount of extra credit for the semester. So anyway, so those will be due, and then you'll just have to turn those in at each exam so that I can see that you're meeting weekly as you go. Any questions about that? If not, then let's go ahead and get started. Well, as far as lecture material, this is a possibility, or this type of question is a possibility on your exam, and so that's one of the reasons we're covering it. I would say this is not a typical question, but it does tie together a lot of things that we've been doing so far. And the first one we'll do, and we have 2 pages to do it, and then there's a companion problem as well, if you'd like to. It says when 15 milliliters of 0.10 molar barium chloride is mixed with 10 milliliters of 0.10 molar silver nitrate, what are the concentrations of all aqueous species after the reaction occurs? Now, if you had this question on your exam, it would actually have the balanced reaction right here, and the balanced reaction would take barium chloride plus silver nitrate, both of which are aqueous species. And I could, as a separate problem, give you these 2 reactants and ask you to tell me what the products are and do an overall total ionic and a net ionic equation. That's a fine question, but I wouldn't pair that with the things we're doing here. But for a double replacement reaction, you're going to switch the positive barium 2 plus with the nitrate to make one of your possible products. That would be barium nitrate. The other possible product is silver chloride. Remember when you write these products that you have to remember that charges balance. Silver is +1, chloride's -1, so it is silver chloride, Ag. Cl, and as such, that is my favorite exception to the solubility rules. It is a solid, whereas most chlorides, bromides, and iodides are soluble and therefore aqueous. It's not balanced yet. I think we need a 2 in front of the silver nitrate and a 2 in front of the silver chloride, and I think that should balance it. This is a double replacement reaction with a precipitate. Now let's actually talk about the question, what are the concentrations of all aqueous species after the reaction occurs? Well, I can tell you what, we're going to form a solid, and so the first thing we need to know is that the silver ions and the chloride ions, some or all of them will no longer be aqueous. Okay? So their concentrations will decrease as we go through this process. And we have information about the moles of barium chloride because we have milliliters and molarity. That'll give us moles of barium chloride. We'll have the same information about silver nitrate. And so this is a limiting reactant problem. And so what I'm going to do to start this problem is I'm going to find the moles of silver chloride that can be produced. Find moles of silver chloride that can be produced. And let's see, I'll put LR there because this is a limiting reactant problem. So I'm going to do it twice. I'm going to do it for my barium chloride. I have 15 milliliters, that's 0.015 liters. Liters times molarity, well, 0.10 moles of barium chloride per liter of solution. Then use my 1 to 2 mole ratio to find my moles of silver chloride. Where I went ahead and set up the other one, same type of procedure. Let's see. Doing this in my head, hopefully it's right, fingers crossed. I get 0.0030, is that right? Yes, good, thank you. And that's going to be moles of silver chloride. I get 0.0010 moles of silver chloride based on the silver nitrate. How much silver chloride, how many moles of silver chloride can I make?
0.0010 moles.
Right, 0.0010 moles. So that's the amount of silver chloride I can make. My limiting reactant is silver nitrate. Are you with me so far? Right, nothing new here. The new part is going to be this concentrations of all aqueous species after the reaction occurs. But we want to check in. So far, nothing strange. Okay, so let me summarize so far. So 0.0010 moles silver chloride made. Silver nitrate is limiting reactant. All right. Now what I'd like to do is instead of thinking of them as compounds, we're going to actually think of them all individually. So I know I have a little bit more room here, but I think I'm going to need to go on to the second page. And I'm going to set up a little table here that's going to have each of my individual ions on it. So barium ion, chloride ion. Silver ion and nitrate ion. And as a little hint, and this might help for the exam, and it's a general rule for Chemistry 400, anything with a charge will be aqueous in this class. Right? When you get to OChem, things get a little more complicated, but when you're writing species, if it's an aqueous species, or if it's got a charge, it's going to be aqueous. It's going to be part of an ionic compound. All right, so these are all aqueous, and we could show that. Now, I'm going to set up a little table here. I'm going to have moles at the start, change in moles, and moles at end. And we've done similar things like this, not with ions, but we've said for the excess reactant, how much do we start with, how much do we change, how much do we end with, to find what we call the leftover. Okay? And this is a table. Now, I'm going to come back here. If I come back here and I ask the question, how many moles of just barium do I have? I would multiply these two together, and then there's one barium, and so it would just be the same number of moles. So can you see that? How many people can see that? Good. All right. So what I'm going to write right here, in red even, is just by multiplying these two together, I get 0.0015 moles of barium. Right, because that's the moles of barium chloride, 1 barium per barium chloride. And that's my start. Now, and this is actually a continuing theme. Now that we know the moles of either barium or barium chloride, how many moles of chloride do we have? What's that? Well, so just from this, so we're still going for the beginning, we know there are that many moles of barium. We know that there are twice as many moles of chloride. So just whatever this number is times 2. Are you comfortable with that? 0.0030 moles of chloride. And again, you've seen all of these parts actually. We've done on the homework 3, there was what's the sodium ion concentration in a solution of sodium sulfate, and you had to multiply it by 2 because there are 2 sodiums per sodium sulfate. Well, now we'll do silver and nitrate here. So math is pretty easy. I like math with all ones. And I'll do these two in blue, although I can't promise I'm going to keep my color scheme. So it's just 0.0010 moles of silver nitrate, and the same moles of silver ion, and the same moles of nitrate. And that pen doesn't even work, so I'm not keeping that one. So it's that many moles of silver just by multiplying these two numbers together. Any questions so far? Okay. Now, let's check in here. If we were to write a net ionic equation for this, what 2 species would be in it? Ag plus, thank you. What was the other one?
CL minus.
CL minus. How many people are comfortable with that? Many of you. If not, that's a great thing to get comfortable with. The thing that forms the solid phase, which is forming the ionic compound and the ionic bond, those are the ions that are going to show up. And barium and nitrate, those are going to be your spectator ions. If not, then I'm going to put that the change in moles of barium, and maybe what I should do here is change in moles. I mean, I don't know how else they'd change, but I could further say change in moles due to reaction. I mean, that's the only thing that's happening here, but due to reaction is just 0, because barium is a spectator ion. It doesn't participate in the reaction. There's no change. 0 for nitrate as well. Okay. Now here comes the somewhat tricky part, or what I would say might be the tricky part. Between these two, you have more of one ion than the other, and yet they form AgCl. And we know how much AgCl we're going to make. And so when I write 0.0010 under both of these, it's because that's how much silver chloride I'm making. Okay? So, when my color scheme shot to crap, but the same number goes there because I'm making the same amount. And I don't have to use up all of my chloride. Yes, Jason?
He's asking for change in moles when CL be 0.002 and silver be 0. There's no change in the silver moles, but there is in the
Good question. So let me come back to this number. This number is the amounts of silver chloride made. And another way of thinking about it is it's the amount of silver and chloride ions that are reacted away. So made by reaction. So I don't know if that answers your question at all, but it's like,
I see now.
and one of the things we find out through this process is that when we find that silver nitrate is the limiting reactant, we're going to react away as much silver. The nitrate doesn't react at all. It's just a spectator. So really, the silver ion is our limiting reactant in silver nitrate. So I'm going to put a minus sign here. Minus signs for all of them because they're all reacted away, or that's the one we get. And then I do the math, and the math's not too bad. And those are my moles at the end, and what we find is, so Ag plus is exhausted or used up completely. That's really what we're using up. Let's write used up completely. That's what I'm going to write anyway. Maybe we want to save exhausted, or maybe we feel used up too as we prep for all our midterms this week and next week. How many, does anybody have more than one midterm this week? Some of you? Yeah. And then the rest of you have jobs and family. I know, it's exhausting. I was at the dump this morning. Yoho County landfill, dropping off stuff. So that was fun. Anyway, okay. Now, we were talking about this morning, and I want to bring this up again. So it says specifically after the reaction occurs. And so when we want concentrations after the reaction occurs, that means we always need to total up all the volumes to get our total volume when I calculate my concentration. And then on the homework, there are some problems that say, what was the concentration before the reaction? And then you just used part of those. Okay? And so those words are telling you which one to use. This says after the reaction occurs. I'm going to start with my barium ion. I'm going to use my square brackets. And now I'm going to do my concentration of barium. I know my moles. I'm going to put it over my total solution volume to get my concentration. And I guess I'll write that out. So moles, barium left over, or at end. Divided by total volume, and I have my moles there at end, and my total volume is going to be 25 milliliters, 0.025 liters. And my final concentration of barium is 0.06. So 0.06. And that's a molarity, and that's barium. 2+. And so the barium didn't react, but whenever you mix two solutions together, that barium, even though it's a spectator ion, its concentration did decrease. Sort of it was diluted, because it didn't react. Any questions about that? If not, then it's the same sort of process for chloride. I get 0.080 molarity. My molarity of my silver ion, 0, donut, goose egg. Zero. No moles left. And then finally my nitrate. I get 0.040. So that is a big problem. I can tell you, it is not the last problem on the exam. I've written the exam now, and I don't usually talk about it once I've written it, but I can tell you that this particular problem, while a good example of like a long problem where you're putting things together in a slightly different way, is not the one you'll see on your exam. But we have more fun in store for you. But this problem has a double replacement reaction, it has limiting reactants, it has ionic moles and concentrations, and then it's divided by the total volume. So there's a lot of things we've already done in this class, and we're sort of repackaging these. Any questions about this? Well, so I gave one other exam hint this morning, and so I'll talk about the exam. The format is very similar to previous exams. I would say the one thing that there are I think 12 multiple choice, which is a couple more than there usually are, right around that. And one of the multiple choice, just like one of the homework questions on homework 4, more than one answer is possible, and it says circle all that are correct or circle all that are incorrect. And it's in bold. Pay attention to the bold stuff. Let's see. Yeah, good. Okay. With that, then, with this, we are now finished with Chapter 4. Homework, remember, will only be collected until 12:30:00 on Wednesday, homework 4, or any time before that. And at that point, I will be starting to pass out the exams. So please plan on being here. If there are no questions, then we will put this away and start on Chapter 5. For Chapter 5 is all about gases. It turns out that in many ways, because the gas particles are relatively far apart, gases are the easiest pure phase to understand in depth, and that's why we're going to start there. Now, how many people have done gases or studied gases in a chemistry class before? Not that many, but some of you. So, and gases is where things really start to get real, because it's new material, like almost all of it. For most of you, anyway. And even for those of you who have seen it before, we may or may not go to a deeper level. But gases in particular, so I've got a picture here, how high temperatures affect flying. And what it's talking about is that higher temperatures, there are less molecules in the air, and that means because lift for airplanes deals with the wing cutting through those air molecules. So as temperatures get higher, say due to global warming, planes are not being able to take off. That's what the point of this article was. And it's related to the number or the density of the air molecules. And I don't know if it says where this is from. I mean, I know it's from the New York Times, which, by the way, nice source, huh? But I think this was a couple years ago. In the summertime at Phoenix, I think, or Tucson, one of those really hot cities, it got to like 126. And the rules are that certain sized airplanes aren't allowed to take off above 123 degrees Fahrenheit. So they grounded the planes. Some of them, the bigger ones too. Anyway, so these, these things and the density of air molecules is important, and they're starting to have more and more effects as you go. Another example, we'll talk about this. So as you go to Lake Tahoe, you go higher in the atmosphere. There are sparser than air particles. There's lower density. Lower density means less oxygen because there's lower all of the types of molecules, and then it can be harder to breathe. Anyway, there's lots of examples of how gas molecules and density are important to us. Now I'm going to move over to slide number 2. Gases are composed of particles. This is going to be about the structure of a gas that are flying around very fast in their container or containers. The particles travel in straight lines until they encounter either the container wall or another particle, then they bounce off. There's a lot of empty space between particles. Now, on homework 1, I asked you to draw a picture of the solid, liquid, and gas phases. And I talked to some of you about this. I was pretty lenient about what I allowed, as long as you drew the gas particles farther apart. Okay? Because that's the big thing about gases. And in fact, here's my demonstration for today. I'm walking through a gas. Do you want to see me walk through a solid? Yeah, me too. But in a very real way, the reason I cannot walk through a solid is because the particles are just closer, while for the gas, they're far enough apart. All right, so over on this side, I'm going to draw my gas in here. And the rule of thumb is that whatever size particle you draw, the next one should be 10 diameters away, approximately, which is a lot of space, a lot more than most people drew. So there might only be 3 gas particles in this entire box. That is how much space there is between gas particles. And it's hard to tell, but with 3 gas particles, they're also randomly positioned in the space. There's no order in the gas phase. And they're moving very fast. And those are speed lines, and it's sort of, it's not an art class, but imagine this is one frame of a comic strip about gases, and this one just bounced off the wall. And this one's headed towards the wall, and who knows where this one's headed. And maybe this one's a happy, no, that's too comic strip. Now, that's a gas phase. Ten diameters between particles, and that's an average. I mean, you can imagine that when you pump up your bicycle tire, that as it gets to 40 or 50 psi, that pressure is created by pushing the gas particles together. And so it might only be 8 diameters, a little less. So it's what I would call an order of magnitude estimate. They're not 1 diameter apart, and they're not 100 diameters apart, but they're about 10. Now, by comparison, if we were to draw a solid, you should draw a question. Bodhi.
So if you increase pressure, they get closer to each other?
If you increase pressure, they get closer to each other, yes. And
gases can be compressed unlike water?
Gases can be compressed, unlike solids and liquids are like water, yeah. And and you could say, like, so here we are with the layers of the chemistry onion. In Chem 400, solids and liquids are incompressible. And that's actually a very good approximation. But if you tell a chemist something's incompressible, the first thing they want to do is compress it. Right? Engineers too. Like, oh yeah? And then you compress, and then you're like, well, what about a rubber band? That's a solid. I can compress that between, So, but to a first approximation, solids and liquids are incompressible. And rubber band, I mean, why is it compressible? Because there is a little bit of space between the molecules. Solid has 2 things, 3-dimensional order and effectively touching. Although, what does touching mean at that level? So I know it's a tiny picture, but there's less than a diameter, much less than a diameter part, and there's three-dimensional order. So I'll say 3D order, essentially touching. And now I'll draw a picture of a liquid. And what I like about liquids is they're sort of an intermediate phase. They're always between solids and gases, and in some ways they're like a solid. And the way that they're like a solid is the particles are essentially the same distance. Maybe a tiny bit farther. Are you familiar with the fact that ice floats? Ice floats, solid ice, because actually the liquid particles are a little bit closer, which makes the liquid more dense. There's your, and that's few of very few materials. But that's an idea of how closely spaced the solid and the liquids are. So I'm going to draw these, well, my liquid's in the bottom of a test tube of some sort. And so I'm going to try to draw them with essentially touching, maybe a little farther apart, but with no order. So something like that, and you could say, well, it's in the bottom of a really tiny test tube if you can see the atoms or molecules, and so the sides of the container create a little bit of order, but we'll neglect that. But a liquid is very like a solid in the spacing, and it's very like a gas that there's no order. That's what it means to be a liquid. It always exists at intermediate temperatures between a solid and a liquid. Although we could talk about that too. But that's pictures of the three phases. Any questions about that? Yeah.
So, say for example, like wood floats because it's less dense than a liquid is on, correct? And then like second or reactions that precipitate sinks because it is
More dense.
than a liquid it's in.
Yep.
Okay.
Yeah. And this idea about why solids and liquids are incompressible, because the spacing of the atoms or molecules is that close. So, in fact, have you ever heard of this guy, David Letterman? He used to have a talk show back in the day. He used to do this bit called Will It Sink or Will It Float? It was all about density. I mean, who knew the guy was into science? Okay, so there's pictures of the phases, and 10 diameters apart, moving very fast here, moving slowly, really not moving at all. Although, even in a solid phase, the particles are vibrating back and forth. So those are vibration lines, and so there is movement. And in chapter 5, and really for the rest of the course, a lot of what we're talking about is this idea that ionic and covalent bonds and intermolecular forces, those are forces of attraction that bring atoms and molecules together. And temperature, as you get to higher and higher temperatures, you have more and more energy, and higher temperatures break the particles up. And there's this definite relationship with that. As the gas particles move and strike a surface, they push on that surface. If we could measure the amount of force, the total amount of force exerted at any one instant, we would know that the pressure the gas is exerting And for here, I want to do number 2 next. And number 2 is going to be the physics definition of pressure. Which is that pressure is a force per area. And then what we need to do is describe what's the force. And the force is going to be force of collisions of gas particles. Force of collisions of gas particles. Divided by area of collision. And oftentimes that'll be the area of the container. So the area of collision or the area of the container. And so when I draw a gas particle colliding with a wall, in a very real way, that is what creates pressure. Now, are you familiar? So there is an atmospheric pressure. Does that sound reasonable? Do you know what the atmospheric pressure is in pounds per square inch?
Is it like 15 point something or 14?
Very close.
14.01.
Close. It's generally it's 14.7 is what I usually use. Some people say 14.69. So atmospheric pressure is 14.7 psi. PSI stands for pounds per square inch. Pounds per square inch. That means if you were to draw a 1-inch square on your arm, that gas molecules from our atmosphere are colliding with that 1-inch square with 14.7 pounds of force. And in fact, so it's actually, our bodies have been made to use that because the bones go down the middle and the flesh is on the outside. And so the only thing keeping, or basically the only thing keeping our flesh on our bones is that pressure. And so what happens when you go to space? Is there any pressure? No. So what happens? Your flesh starts to expand, right? Because there's nothing holding it there anymore. And that's an issue. And so what do? Then you need clothing that holds your flesh onto your body. Or you need to pressurize the atmosphere to create that atmospheric pressure. Yeah, no, so that's, that is what keeps our flesh on our bones. Very real life. Okay, any questions about this? All right, well then, so the next thing we're going to do, like you can't see gas particles typically, but you can see their effects. That's what I'm trying to motivate for you, is that by looking, so there's 14.7 pounds per square inch. So how do we measure pressure? And basically the oldest way, and the way that we still do it, oftentimes, is using a barometer. And even if we don't, we still use units like pounds per square inch, or actually we use units of millimeters of mercury. And the units here are millimeters. This is a picture of a barometer. And in this barometer, there's a couple things going on here. The gas particles are colliding with the surface of the mercury. gas particles are colliding with the surface of the mercury. Mercury is chosen because mercury is a liquid under atmospheric conditions. We looked at our periodic table. It's blue. The other liquid is bromine. Not a very fun thing to use. Chemists are practical people. It turns out that bromine would then just all evaporate, but the mercury, it takes a very long time for it to evaporate, so functionally it's much better. They collide with the surface of the mercury to impart a pressure. Let me say one more thing, Bodie, and then I'll take your question. Vacuum. What does the word vacuum mean as far as pressure?
Lack of pressure.
Lack of pressure, right. So here there's a vacuum, here there's no pressure. Or essentially no pressure. Bodie?
Where does gravity come into this? Because if the atmospheric pressure is pushing down the mercury, is that technically the force of gravity pulling the atoms down?
So I reached for my wallet because Bodie's a plant. I owe him $5 because that's exactly what I was about to talk about next, is gravity. I don't actually. But good news, I don't have my wallet either. So yes, gravity. And so what's going to happen here is there's no pressure up here, but the higher this gets, the more gravity acts on it. And so what we've really got in a barometer is what's called a force balance. And a force balance means that there's a pressure per area, so times an area. Force is pressure times area. There's a pressure pushing the mercury up the tube. Let's say this. It's pushing it down. There's nothing here to oppose it, so it ends up pushing it up the tube. And then gravity is what pulls it down. So we're using gravity and this open pull of mercury, and there's a pressure difference between them, or a force difference. So force balance is really the atmospheric pressure pushes the mercury up the tube. Gravity pulls the mercury down the tube. And then as the atmospheric pressure changes, if the pressure of the atmosphere goes down a little bit, then the level of the mercury goes down because gravity is the same, right? So that's how this becomes responsive to atmospheric conditions. If you look, so I'm very interested in weather. I always want it to rain in California because I think we need more rain. And you can look at the atmospheric pressure to tell you when there's high pressure, low pressure, and when there's a higher chance of percentage chance of rain, for example. And what happened was this definition, 760 millimeters, was found to be the atmospheric pressure at sea level. And so that was what was called 1 atmosphere. Although if you look at your phone, maybe the pressure, or if you look at your barometer, or the phone tells you what the barometric pressure is, it might be 745, 755, 765 millimeters of mercury, depending upon, let's see, when it's hot in Sacramento and Davis, that's usually a high pressure system. Did that answer your question, Bodie?
Yeah.
Thank you for asking. Any questions about this? Any other questions? Good. And I'll just remind you that what is creating this pressure is literally collisions of gas particles bumping into this fluid right here. Next question, what would happen if the column of mercury were replaced by a column of water? Well, here's our picture. Let me tell you a couple facts. One is that the density of water (1.00 gram per milliliter), while the density of liquid mercury (13.6 grams per milliliter). Now I'll come back to this force balance. For the force balance, the gravity enters in by acting on the mass. So if the mass is 13.6, or let's say that's the density, and therefore the mass is 13.6 times greater for mercury, let me put that another way. If water is 13.6 times less dense, in order for gravity to have the same effect, would this tube have to be larger or smaller? Much larger. It'd have to be 13.6 times larger. And so, barometer with water would have to be 13.6 times larger. (13.6 times longer tube). (760 millimeters). That's let's see, 1,000 millimeters in a meter, so that's 3/4 of a meter. Push that up 13.6 times. It turns out it has to be about 30 feet. And physically, that's not realistic to create a 30-foot glass tube, although I did see at one college that I visited, they have the full 30-foot tube. It's awesome. I very much admired them for doing it. But let me ask the question another way. Okay, so if, let's say the changes in the pressure are 10 to 20 millimeters of mercury. How much would that be for water? It'd be 13.6 times that. So it turns out, and we'll come back to this in our last chapter of the semester, but when you use water, if there's a movement in the water, it's very sensitive to pressure. So you can record small pressure changes using water. So you do need 13.6 times. Not practical for a barometer, but because the water is so sensitive to small changes in pressure, it will be practical for other things. And while this is atmospheric pressure for barometers, if you've ever heard of osmotic pressure or osmosis, that's where you measure that with water. We'll talk about that later. Leo?
Quick question, I think I'm getting ahead of myself, but at the top of that 30-foot water barometer, wouldn't the water boil because the atmosphere is so low? Like the vacuum?
Yes, no, good question, because there's no pressure up there. That's a good question. So what I imagine is they probably use a variety of techniques to keep it from boiling.
Okay.
Let's see. Oh, practically speaking, so even mercury has a tiny bit of, it has a vapor pressure up here. Water has a tiny vapor pressure as well. And what you want to do is, as long as it's about room temperature, you can correct for that.
Okay.
Yeah, there is a little tiny bit of pressure. I'm going to keep my barometer up there and go to the next slide on this side. What happens to the height of the column of mercury in a mercury barometer is you climb to the top of a mountain. Well, this is a picture of as you go to higher and higher altitude, the sort of a pictorially the density of the air molecules, and then as you get to higher and higher altitudes, you do get lower and lower air pressures. So if you're at, I don't know, how high could we get? We're probably down here into the 10, 20 kilometers. It's measurable difference. I mean, this is almost space and beer, it is space. So, but my point being, what happens to the height of the mercury in a barometer as you go to higher and higher elevations? It's lower because there's less molecules that are still moving at the same speed, but less molecules means less collisions, means less pressure. So, and that's what I want to write here. You can write the same. So, less molecules equals less collisions equals less pressure. And you get a lower height of mercury because there's less pressure pushing it to 10. Any questions about that? All right, I think that's, yeah. Now, units of pressure. We've talked about pounds per square inch already. We've talked about millimeters of mercury. We've talked about or mentioned atmospheres. So that's just a unit that is for atmospheric pressure, but it has a strict definition. We haven't talked about bar and we haven't talked about pascals. 1 bar or bar. So bar is what's called the SI unit. System International. So it is like the uber metric unit. So 1 bar is actually very close to 1 atmosphere. And we'll have more to say about bars down the road. But pretty much for this class, 1 bar is approximately equal to 1 atmosphere. And we will talk more about that, but you can see they're very close. Pascals actually talks about newtons and meters squared, and we do talk about that. Let's see. I think as far as unit conversions, the main one that you have to know is I typically give you information in millimeters of mercury. You will have to convert it to atmospheres. I don't know whether this is on your conversion and equation sheet, but if it is not, please memorize it. Now, of course, this is on your second exam, not on your first exam, but there will be a variety of unit conversions that we can ask you to do. It says a high-performance bicycle tire has a pressure of 132 psi. What is the pressure in millimeters of mercury? We can use our unit conversions over there. We can say that 14.7 psi. is equal to, all those things are equal to each other. 14.7 psi equals 760 millimeters of mercury. Everything's got 3 significant figures. Incidentally, as I grade the homework, what I realize is that sig figs is too much to write. So if you see SF from now on, it's shorthand for significant figures, SF, not San Francisco. Go Giants. But, anyway, and none of you will ever see that because you'll always give me on your exam on Wednesday 3 sig figs for all of your answers, unless it's a PH, and it's got 2 decimal places. Good. Anyway, so as we do this, I multiply this out. You get 6,820 millimeters of mercury. Which more or less ambiguously put for 3 sig figs, 6.82 times 10 to the third. After your exam, should you want to come back and practice on unit conversions, we've got another companion problem. That's what CP stands for. Now let's talk about manometers, not manometers. That's a whole different class. Manometers are U-shaped tubes partially filled with a liquid connected to the gas sample on one side and open to the air on the other. An open-ended manometer is open to the atmosphere and measures the pressure difference between the pressure of a gas and atmospheric pressure. So here's an open-ended manometer with a gas sample on one side and atmosphere here. And there's our liquid mercury. What can we say about the pressure of the atmosphere and the pressure of the gas since the levels are equal? The pressures are equal. These two pressures are equal. And so for this particular situation, the pressure of the gas, that's a capital P for pressure, and GAS is the subscript. P gas equals P atmosphere. I don't write atmosphere there, but it's a little bit of a long subscript, so I will oftentimes use ATM. Sometimes you'll also see external pressure. External pressure just means outside pressure. And so sometimes you'll see P external. Now let me sketch another situation over here. It's not an art class, but that's supposed to be just like we've got over here. I've got a gas in here. This little thing, this valve, which could be open or closed, I draw as a little T through the tube. Well, it's certainly not an art class if that's a picture that I'm drawing. My question for you is, based on that drawing, which has a higher pressure, the gas or the atmosphere? The gas does. So gas has higher pressure. So the pressure of the gas is greater than the pressure of the atmosphere. We can do better than that, though. We can actually measure I'll note again, these little dashed lines, those are liquid mercury. We can measure the height of the mercury, or the difference in the height of the mercury. And we can say that the pressure of the gas, being the greater number here, pressure of gas equals pressure of atmosphere plus the height of the mercury. And let's say you measure that height in millimeters of mercury, then right away you can make a comparison. Otherwise, you could measure it in inches and convert them to millimeters. Everything's fine. Any questions about that? Good. All right. Now we come to our first gas law. The first gas law is called Boyle's law. I'm actually reading a book that mentions Boyle. Boyle was one of the founders of the Royal Society, which is the sort of one of the scientific societies in England. And when Boyle was alive, it was the 17th century, and England sort of, for better or worse, in many cases worse, ruled the world, right? The sun never set on the British Empire back in the day. Turns out Boyle had a large part in the science of that time. Boyle, Newton, you ever heard of Isaac Newton? Boyle was his contemporary, and Newton read Boyle. Like, he's like, well, I want to figure out what science is. I'll read one of the best known people in England, who is Boyle. Although recently I'm reading a book, and it talks about how Boyle contributed to the enslavement of African Americans even in this country, because he had pretty racist views. And so, anyway, he's my picture of Boyle as a scientist. I think a lot of his work, not so much of some of his own work, or I completely negatively think of some of his own work. Anyway, but now Boyle's law, the experiment. You have a situation where you have a volume of gas. And you can see that you have a pressure difference here based on the height of the mercury. You add more mercury, that means there's more pressure and the volume of the gas decreases. So, increase pressure, decrease volume of gas. And whenever you increase one thing and decrease another thing, that relationship is called an inverse relationship, inversely proportional. Let me show you what some data might look like. Volume of air versus pressure, what you can see is as you increase pressure, the volume of the air becomes small. Now, when I graph things, I like the graph to have a straight line, because then I can add a trend line to it, and then I can fit that trend line, just like lab number 2. Just like so many other things we're going to do this semester, wait, just wait. So what I'm going to do is, no. going to replot as 1 over volume on the next slide. I get a very nice straight line. And what this suggests is that pressure is directly proportional to 1 over volume. We write that mathematically right here. Pressure, this is the lowercase Greek letter alpha, which means is proportional to. Pressure is proportional to 1 over volume. If two things are proportional to each other, I can insert a proportionality constant. That's lowercase Greek letter, or sorry, lowercase, just regular letter, K. And now I'm going to move the volume to the other side. PV equals K, where K is a constant. You know why we use the letter K for constant? Because in German, K, constant starts with the letter K.
Because why use English?
Because why, right. Well, when they come up with it, I guess they get to use it. I don't know. I wonder what it starts with in French. All right, so PV equals K equals constant. Are you familiar with the equation for a line? Y equals mx plus b. What's b in this case? Zero. The y-intercept is, b is the y-intercept, and the y-intercept is 0. So what this really saying is these two are proportional or inversely proportional. Their product is a constant with y-intercept equals 0. The form of the law, what's called Boyle's law, actually says if pressure and volume equals a constant, then you could get different sets of pressure and volumes and end up with P1 V1 equals P2 V2. This is Boyle's law. You do not have to know Boyle's name. All you have to know is how to apply Boyle's law. I believe Boyle's law, or I believe this, P1 V1 equals P2 V2, is on your conversion equation sheet. And so you will have access to that. Does this look familiar? Do you know any other laws or any other equations that go something 1 V1 equals something 2 V2? The dilution formula, M1 V1 equals M2 V2, because molarity and volume are inversely proportional to each other as well. Well, we'll do some examples. Let's see, depending upon how much time we have. In a couple minutes. So now it's time to think about the molecular view. Pressure is caused by the molecules striking the sides of the container. What we're doing here is, so as we go from P equals 1 atmosphere, V equals 1 liter. Well, let's try this. P1 V1 equals P2 V2. 1 atmosphere in 1 liter. If you apply 2 atmospheres of pressure, of course you get 25 liters. Now, pressure is represented here as far as the pushing force on the top by the kilograms. We double the mass. Gravity being the same, we double pressure. As pressure is force per area, the area is staying the same. Here's gravity playing its role again. But here, in the same way that when you're talking about the barometer, so this gas has to be pushing back against this 1 kilogram, and it has to be pushing back twice as much here. So what we're saying here is that there must be, for the same area, twice as much force, so same area, well, twice as much pressure, twice as much force, twice as many collisions of gas particles. If there were no collisions down there, then this should fall all the way to the bottom. The only thing holding that up is collisions of the gas phase trapped inside the system. Anyway, I have mentioned the collisions a lot. You can see here too, by the way, that as you decrease the area, they are getting closer together. We talked about that, but they're still pretty far apart. Any questions about this? A cylinder with a movable piston has a volume of 7.25 liters, 4.52 atmospheres. What is the volume at 1.21 atmospheres? I erased Boyle's law. I'm going to write it again. P1 V1 equals P2 V2. My V1 is going to be 7.25 liters. My P1 is 4.52 atmospheres. What's a little weird about this is, see that word at in there? It's telling you to multiply these two numbers together too. It's not of anymore. But otherwise, this is what I politely like to call plug and chug. You know the right equation, or you will. You plug in, you solve for V2. Remember, or you will remember, I know we're just introducing this, as you go to lower pressures, you must have higher volume because they're inversely proportional to each other. And this is one of the things that I've been checking in with people about as they solve the math. What I've noticed is it's very easy, and I do this myself, to mix up numbers as you do all the calculations for this. And that sometimes, it's hard to tell when you've done that, of course, but sometimes it gives you a completely crazy number for an answer. Always check in. And as we come to our first exam, if you get a crazy answer, and you don't know what the problem is, or you think it might be crazy, feel free to say that. Because that's knowledge to me, and you may get points for it. No promises. But on Wednesday's exam, if you solve the problem and the pH is 47, you should write me a note that says, this seems out of the range of pHs that I should get. I know that. Or just, you don't have to write I know that, but just by writing it, it tells me that you understand that something may have gone wrong. Things go wrong on exams. Right? Hopefully not yours, but if they do, and you know it, feel free to write me a little note, that's all. And I mean, if you write me a note that they could have gone wrong, and it turns out you get the right answer, I will never take points off for that. Just anything that looks a little weird, feel free to note it. Okay? The other thing, I've mentioned this a couple times, if at all possible, don't leave it blank. It's impossible to get any points for blank spaces. All right. Anyway, so as I work this, my volume 2 has to be bigger. I get 27.1 liters. One on the next page is a companion problem, and instead of starting Charles' Law, we will stop for today and pick up there next time. Next lecture will be 1 week from today because you have an exam on Wednesday. Any questions? One last note. To take the exam on Wednesday, if you're in the Wednesday morning lab, you have to come to lab. The converse to that statement is if you're sick for lab, you're sick for lecture too. It happens.